All right, so let's get started. So today's topic was, so far we talked about linear mixed effect model, but today we are moving on to logistic mixed effects model. Okay, so this is a schedule up to now, and yeah, we are in logistic mixed effect model, and I'm not sure what topic I should cover, and I ask you what topic will be more appropriate. Then I think almost all of you have, I think I received your email so that you receive some reminder for this session, I guess. And if you wanted to receive email for this session, please email Octavio and me. And today's objective is, well, overview of logistic mixed effects model. All right. Then, so today, well, this time we are going to use again the data set from Brazil. Uriel, can you pronounce this one? No, I'm not confident in pronouncing PNS. This. Well, anyway, Pesquisa Nacional de Saúde. I'm not sure. Anyway, so Brazilian PNS
right.
survey.
Pesquisa Nacional de Saúde.
How many points did I? How many points did I get? 70%.
Yeah, I'll give 9 out of 10.
You are generous. And for this time, it's not only men, but also the data set include women. And you can see this data set on our Google Drive. And this includes a city ID, sex, age category, HT for hypertension. This is the binary outcome, 0 or 1. 0 mean non-hypertensive and 1 mean hypertensive, and BMI. And well, the study aim for this example is to know the association between hypertension and BMI adjusted for sex and age. And here, well, it says logistic of X, Y, I, J equal 1. This means well, YIJ represent hypertension status 0, 1 of person J in city I. So first of all, let's go to exploratory data analysis. And this data set contains data of 27 cities. And well, when we look at this statistic, well, the smallest city contains about 600 observations, and largest data set contains 2008, well, 2,900. So here we don't have too much worry about the sample size. It's we have sufficient number of data, I think, in general. And this is a histogram which shows the distribution of number of observations per city, starting from 500 up to 2,900. Since was the smallest city contains 500 observations, so I do not worry too much about this data set. So first of all, we are going to start assessing the mean component. Well, mean component, we are going to include age, sex, BMI. So we have to check association of these variables or predictors with the outcome variable, which is hypertension. And well, as we did for linear regression, we use lowest curve to explore the association between binary outcome and the continuous predictor. And then when we use logistic regression, it's usually recommended to use logit scale on the y-axis, because this is how we model. We don't model outcome equal equation consists of predictors, but we are going to model logit or log odds of probability attached to linear combination of coefficients. So it's usually recommended to do exploratory data analysis using logit scale, which is shown on the right-hand side. And by the way, on the left-hand side, it's shown using probability scale here. But the problem is sometimes when somebody say logit of prevalence is equal to 0, it's difficult to imagine what we are talking about. Now, well, since the association doesn't look like linear between age and hypertension prevalence, so we may think about categorizing, use age category instead of including age as a linear term. And another option is to include a quadratic term of age, but this time we are going to use a categorical age. So this is how it look like. Well, I think it's okay to me. And well, this is what I mentioned. So these are numbers in logit scale, but these logit scale from 0 to -4 correspond to these probability. Well, probability of prevalence of hypertension. 0 corresponds to 50% of prevalence, and -1, 0.28, 27%, 12%, 5%, 2%. So for this 0 to -4, this is how to say, the number changes by 1 unit, but they are in probability scale, they don't. So this is something we have to keep in our mind. And now, so we finished with age and sex, and we want to assess the association between hypertension and BMI, which is continuous variable. And this one, the graph to the left, and this graph shows the association for men and women. And I thought that these two lines are kind of similar. So I pulled men and women, and I decided not to separate between men and women, but I decided to pull, well, which may be appropriate, may not be appropriate for other cases, but at least in this data set, it seems that they follow similar trend. But here we see somehow it's kind of linear, but it's not completely linear. So I decided to split this curve into two, well, from 10 to 35 and from 35 and above. So I'm going to try to fit two lines, below 35 and above 35. And I fit it, and then I fitted the model, and then it seems that this model goes quite well. And then now we are going to do assessment of variance component. And namely, we want to look at the what are between variance and within variance, or between variability, between cluster variability and within cluster variability. And here are some programs start. When we have continuous outcome, well, this is a very small graph, by the way, but we can use box plot. Well, these are for each city. At that time, well, in the previous one, we plotted box plot of systolic blood pressure for each city. And then from here, well, by looking at how the median fluctuates over country, over city, we were able to assess between city variability. And by looking at this spread, we were able to see variability within city. Hi, Jenny. Hey, I see your hand.
Hi, Goro. Hi, everyone. Sorry for the interruption.
Uh-uh.
I just
go
want
ahead.
to know, how do you decide to to I don't know, I don't know how to say it.
Oh, en
To have
castellano.
this plan on 35. How do you
Ah,
decide to knock this plan on 35?
that's a very, very good question. I think it depends. So you're talking about here, right?
Yes.
How to decide? That's a very good question, and I think two things we have to consider. One is we have to look at the shape of this one, and we have to know where is the most appropriate cutoff point. This is one thing, and the second is, well, say the inflection point is certain value, like a 38.5, something like that, but you may not want to do so because this number that may not say much. I mean, you may want to pick up some rounded number. So I usually consider these two things. And
Okay.
actually, it's a good point. Good point. And when I look at this curve, I saw that 40 is a good point to use. And then I fit the model, but it didn't go well. Well, what happened was this line after 40, it went somewhere, or it went this way.
Okay.
So I saw that 40 is not good place. So I chose some numbers below 40. And when I used 35, it fitted well. So this is the reason why I picked up 35.
Okay.
And also another reason why I picked up 40, because 40 is a cutoff point where this is a 30. This is a cutoff point of obesity criteria, I think.
Yeah,
About,
like obesity grade 2,
obesity.
I think, or 3.
Yeah.
Yeah.
So in this sense, I wanted to use 40 at the beginning. But when I fit the line, it didn't fit on the data well. So and then I moved to 35.
Okay.
Yeah, that's a very good question.
Thank you, Goro.
You're welcome. At the same time, not at the same time. As alternative is we use categories of BMI. This is another way.
Okay, right.
So depending on how you want to say in the paper, I think. So we go back to this separating out variability between and within cluster. And when we use continuous outcome, we were able to do this we are able to use this box plot to see what between city variability and within city variability. But when we use this binary outcome, it's a problem because a binary outcome takes only 0 or 1, right? So when we make box plot, it's always from 0 to 100. So it's not useful. And how to explore this part, this is a challenging thing. And this is a method what my mentor told me to do. So there must be several other ways to do. But this one shows point estimate of hypertensive prevalence per city with confidence interval. This is a contents of this graph. And then by looking at the minimum and maximum level of point estimate, we can see what is a between variability across cities. But within city, it's difficult to know. Okay. But do you have any, well, some of you have done many logistic regression, and I wonder if you have any other way to explore this part. if you have any idea, please let me know. Anybody as of now? No? Tanya is smiling. Okay, let's move on. So this is one way to do it. And then we move on to regression analysis and model checking. And well, analysis plan is very simple. I wanted to make it simple. First, we are going to fit null model, meaning we include only intercept without including any predictor variable. And this is to assess the level of shrinkage and to show how to interpret random intercept. And secondly, we are going to fit this final model, which include two spline term for BMI, sex, age, and their interaction term. And BMI, well, these two spline terms are defined using this formula, but it's confusing, I think, because I wrote out because I needed to do so. But what we have to know is this one, beta 1. Beta 1 coefficient tell us the association between BMI and logos of hypertension when BMI is less than 35. And beta 2, this shows the association between BMI and logos of hypertension when BMI is greater than or equal to 35. If you get confused with these two equations. And well, this is a result of null model. So we have this number of observation, and there are 27 cities. And where should I start? Okay, so this is a coefficient. It's not exponentiated, just a coefficient. And we have estimate for variance of random intercept. So this is a coefficient for the intercept. And from here, we can calculate overall prevalence, which is given by this equation P, where prevalence P is given by, well, this one is an inverse logit function. And we plug in this number here, and we get 0.17. So overall prevalence of hypertension is 17% in this data set. And the estimated standard deviation of the random intercept is 0.21. So this means that 95% of logos of prevalence is expected to be within this number, negative 1.57, plus or minus 2 times this one, 0.21. So this is in log odds scale. So we take inverse logit of this number so that we can talk in probability scale. So 95% of prevalence is expected to be within 12% and 24%, right? And then this is not symmetric because well, these was a confidence interval. They were not confidence interval. The upper limit and lower limit, they were symmetrical in log odds scale, but in probability scale, it's not. Right? The difference between 12% and 70% is only 5%, and the difference between 70% and 24% is 7%. It's not symmetrical because of this conversion of the unit. And well, this is about the assessment of shrinkage. The blue dot show observed log odds of prevalence of hypertension. Well, when I say observed, well, when we have sample, we can just calculate prevalence using the people in our sample by taking the average of hypertension variable. And this is how we get. And the pink one, the pink dots, these are estimated from our random effects model. And as you can see, always these pink dots are, I should say, closer to observed mean. So there is certain level of shrinkage. But by looking at this one, there are not that much because each city has a quite good number of observations. And well, this is in log odds scale, and this is in probability scale, just so that we can imagine better. This is in scale, say this city, the observed prevalence is about 22%, but the estimated one is 21%. So it's not that bad. And let's go to this lower end. And this one, observed prevalence is 12%, but estimated prevalence is about 13%. So it's a difference of 1%. So it may not be that there were not that big shrinkage we have to worry about. But this may happen when cities have smaller number of observation. And this is another way to look at the horizontal axis shows observed log odds of hypertension, and vertical axis shows estimated log odds of hypertension. So if the estimation are the same, we see the dot along this identity line, but you see that these dots are somehow shrunk towards the mean. Well, meaning so these estimation moved up, and these estimation moved down. So there was certain shrinkage, although it was not that big. And as you can see, by the way, the circles are proportional to the number of observation. And when you see, well, when the sample size is bigger, for example, this one, the level of shrinkage is smaller because there are more sample size. Okay. And then ICC, interclass correlation. So this is a general formula for ICC. Numerator is between cluster variance, and denominator, we add two variances of between cluster and within cluster. And they are given by variance of random intercept divided by variance of random intercept plus variance of error terms. But here, in case of logistic regression, this one, variance of error term, it's a constant. So it doesn't change across data set. It's always this value. And we can calculate, we get ICC of here 1.3%, which is kind of small in this data set. Then we move on to final model. This is a model we fit. And well, this is the output again. This is the total number of observation from 27 cities. And this is what we wanted to know because we were interested in association between BMI and hypertension. And well, I did a test to see if these two slopes are the same. And it turned out that it's statistically significant. And if this is not statistically significant, we even don't think about separating slope into two, but we use only one. But since this is, well, visually they were not linear. At the same time, since this test says there is statistically significant difference in slope, in this sense, I'm going to keep this BMI with two spline terms. Also, it's depending on if Also, if this magnitude, the difference in magnitude is 0.03, so if it is not clinically important, we may have option to use only one term for BMI. Okay. Then interpretation of this number. So in a given city, the odds of hypertension increases 1.11 time by 1 unit increase in BMI when BMI is less than or equal to 35 after adjusting for age and sex. So this is a complete sentence if you want to interpret odds ratio in the exam room, but there might be some variability. But when we do when we do interpretation from mixed model, this is an important part in a given city, because we use random intercepts specific to city. And this number doesn't tell us estimate in population, but estimate within city. And well, this coefficient, the interpretation of this coefficient is very similar to what I said for for BMI 1, which was for BMI when the BMI is less than 35. So the same type of, so I don't read because they are the same, only this number and this number changed. And the other thing is this one, constant term. This one doesn't have the same meaning as it had in null model. When we have intercept only model, this one, the constant term told us the overall prevalence of hypertension. But now, since this model contains categorical variable, which are sex and age, so this constant term is overall prevalence among different population. And what is a different population? In this case, men of 20 to 29 years old. And if you want to get the estimated overall preference, we have to do linear combination of this value and this value. Then we move on to model checking. And principally, we can do so by repeating the same or similar assessment method for the exploratory data analysis, but this time based on predicted probabilities, not observed 0-1 outcome. And there might be many other ways. This is what I usually do. So first of all, let's look at the hypertension versus sex and age. Both of them are categorical. And this table shows the observed prevalence at each combination of age and sex. Well, this is from the data. And this table shows the same quantity, but based on predicted probability. And when you compare this table, you realize that they are almost identical. Maybe only this one, it was 4% here, but now 3.9%. And apart from that, they're the same actually. And well, this is how we can assess using table. And on the right-hand side, you see the graph. This is the lowest curve to see if there are any difference between observed, association based on observed value and association observed based on predicted probabilities. And they are quite similar. I do not see departure of these two lines between observed and modeled. And we move to BMI, which was continuous variable. And well, on the left-hand side, the result is shown in a Logistic scale. And here, the dotted line is observed and solid line is modeled. There are some departures here at lower end and higher end. But at the same time, where BMI below 20 is possible, but below 15, it's very uncommon. At the same time, BMI more than 50, it is a very extreme. So I may not worry too much about it. And the same graph, same type of assessment was done using probability scale, and they look fine for me. So this is actually the end of today's session. And so we reviewed the model fitting and checking process for logistic mixed effects model. And principally, the process is very, very similar to those for linear mixed effect model. But because the outcome is binary, method for data exploration and model checking is somehow limited. And the last thing we may want to be careful with logistic model is coefficient from the mixed effect model show association in a given cluster. And in the example, we had given city, not something we observe in the entire population. So this is something we have to be careful when we interpret the coefficient, although many people mixed up this part. So do you have any question?
I have one question, Goro,
Hold on.
about the prediction you made in the model checking section. You predicted for all the cities together, right?
Yeah.
Would be also good to do it by city, this, or is not necessary if you look this in all the cities, the prediction corresponds to the observed?
That's a good question, and other people can chime in. And well, here, well, depending on the sample size as well. Like in case of this data set, well, if you remember, each city has 500 observation or more. So in this case, we may be able to do model checking in this way. But in some cases, or in many cases, sometimes we have very, very small number of observations, like 5 observations per city or something like that. So in this case, since we don't have enough number of observations, we won't be able to do this type of assessment at city level. This is one thing. And the second thing is here, the main purpose is to see overall fit. And this is another reason why I didn't do at city level.
Okay.
But I think it's depending on your main question as well. And here we wanted to know the association between this hypertension BMI in general, accounting for clustering type of data. But if you are interested in getting city specific estimate, it may be a different story. And we may want to do model checking by city.
Okay.
No.
Thanks.
You're welcome.
Goro?
Yeah. Yes, Jenny.
I have one question. If we have an city level exposure instead BMI, the procedure is the same, right? I mean,
it's the same.
The random effect, it's at the city level, and with that, we are like completed the analysis. Okay.
I think so. But if there are several people who do a lot of analysis. So if anybody have any comments to Jenny's question, please speak up.
Okay.
So well, my response is we can include as other variables.
Okay.
Uriel?
Well, I actually had a comment about the ICC
Uh-huh.
that you showed. It's in logistic models, we usually show the MOR, the median odds ratio.
Uh-huh. Instead
I
of
mean,
ICC.
yeah, it's a similar formula, but I think it's more. I don't know. I mean, I wouldn't use one or the other, but I like using both of them. You know, I mean, both the ICC and the median odds ratio, because I think the median odds ratio gives us a very interesting interpretation here in the logistic context as well.
And a question for you, or two things. One, well, I personally don't use the ICC for logistic model. Well, I usually don't look at the well, I don't do separation of variance. But when do you use MOR or when do you use ICC, or you always look at two of them and then because two of them capture different thing? How do you interpret these two things?
Well, it's hard to say exactly, but most of the papers and most of the people that are looking at the analysis of logistic models, they prefer looking at the median odds ratio because it's readily interpretable to them. But I would use the ICC. I only use it for model checking, actually. You know, just look at a lot of measures to see if everything's okay. But when reporting and commenting about the model, writing about the model, I usually only report the median odds ratios.
Okay. So when you use MOR, does it have more advantage over ICC? ICC, the problem is here. And the okay. Or you
No,
look
I
at
mean,
both.
I simply, you know, I mean, I like the interpretation of the median odds ratios. And I
Okay.
like comparing them across models to see if the model is capturing less or more overall variability across across different sequences of models.
Okay.
I would mostly use the ICC to see if the between cluster variances are too small compared to what you would expect for the model, but that's pretty much about it. Because the within cluster variability here is always fixed to pi squared over 3. So,
Yep. Thank you, Uriel. And well, actually, I haven't used median odds ratio. This is, am I saying correctly? Median odds ratio.
yeah.
Okay, so I haven't used that one, so it was a new information for me. And thanks for mentioning about. And you mentioned also many papers use median odds ratio instead of ICC to report. That's good. Good to know. Thank you, Uriel.
Yes.
Any more comments or questions? Okay, so we finished this one, and then we finished this one, meaning this is the end of the session, and the next one is going to be December 10th, Friday. But there are not many people here today, but still I haven't decided which topic I should cover, and since you are a frequent participant in these sessions, I wonder which we should cover. Well, one is Poisson negative binomial model, where we looked at linear, and now today logistics. So the next one is going to be Poisson negative binomial, so that we can cover count data. And the second one is how to get relative risk instead of odds ratio when the outcome is binary. And this is something I hear a lot, especially with Salva project. Previously, I was always using logistic model, but here, since the outcome is very common, and people misinterpret odds ratio as risk ratio. So I want to calculate the thing in relative risk. So I saw that this is another option we can cover, or something else. And I wonder if you have any preference in terms of topic coverage.
I would prefer Poisson and negative binomial model, but Uriel says that you have a session about that, but not mixed. I'm not sure in the chat. It was a previous session, or
Remember the session about Poisson?
Yeah, I think it was actually the first session when it was part of the live events study group. We did a Poisson negative binomial over dispersion, but you didn't cover the mixed effects, the random intercepts part. So
yeah, well, it was when to choose which, right?
Yeah.
Yeah, this was what we discussed. Although apart from that, there won't be big difference in what we do actually with the logistic one, and the interpretation is going to be similar. Okay, right. I haven't decided yet.
okay, but I think that session is recorded, no? It should be in the Salurval site, no?
I think so. I don't remember. And previously I was not able to manage Zoom well. Well, still I'm not able to manage well, but for this list, I'm not sure if I was able to record or not. But yes, good flow is a Poisson negative binomial. And the Kevin mentioned Simpson's paradox.
No, I was talking about the Jordan's question about that what happened if we were just analyzing one city and like we using the prediction model. And I thought that maybe it will not converge well enough for just one city, and maybe that was like kind of a Simpson's paradox, that it will be good enough at the higher level but not at the individual level.
Okay. But yeah, that's quite true. That's quite true. And this is another reason why we do regression model, right? And when we don't have enough data for certain category, but by grouping all together, we cannot do stratified analysis, but by combining all of them, and we can do the analysis. Yes, what you said is quite right. At the same time, today I said I use this city prevalence, but what we can get from this data set may not be actual city prevalence, because these are based on survey data, and survey data I'm not sure about this PNS, but many sample, they are not done as the data that will give us representative data at L2 level, for example. So it's a prevalence in quote. Okay. So thank you. Thank you for your contribution. And hold on, say my vote is for relative risk. Okay. So but yeah, about the Uriel's comment, yes. At the same time, but we use a random effect model because we need to account for clustering structure of the data. Right? Not our intention is not to estimate prevalence, but to account for this clustering. So in this sense, this is fine. And what I'm not sure is, I think many of you participate in survey group discussion. So what I always do not know is how, say, when we do ICC analysis and we were talking about the proportion of between and within cluster or within city, and how much we can tell. This part I do not know. I have uncertainty about it, but you may have answer for this. Do you have anything about this? About the representativeness of data and what we can tell from multi-level model when we use a survey data set. Yeah, so this is something you can brought up to the survey group discussion, I think. And I remember that yesterday, Ale mentioned about this something related to this topic as well, how our data can be representative at certain level. Okay, right, thank you very much. And well, Friday, the date and day is fixed, but for next year, I haven't fixed yet. And do you have any preference about the date and time? Although some of you, I think some of you teach classes and then your schedule change next year. So somehow it's difficult to say, but I wonder if you have any preference about the timing of this session.
As I usually teach on Thursday, but I am thinking to quit because I need more time. So, I hope I can you continue Thursday.
Thursday is better or Friday is better or any days? Okay.
Well, for me, like I have complete availability. I'm not taking classes anymore, so either one, it's fine.
I vote for Friday.
You don't want to go for weekend earlier? Hold on.
Yeah, well, I think, yeah, in any day, but Friday I think is more relaxed. And probably Thursday is like I still need to catch up on stuff.
Okay. Tanya said you have class on Thursday?
Yes, usually. Yes.
Usually.
Yes. I prefer Friday, but if it's not possible, it's not a problem. I try to see the recorder.
Okay. All right. Thank you. So this is, I think this is the end of the slide. Yeah, this is the end of the session, and thank you very much for participating. And after you participated in many meetings this week, and I will see you next month in December.
Thank you, Goro. Thank you,
Thank you,
everyone.
Goro.
Thank you.
Yes, Goro. Bye.
Bye.
Goro.
Thank you. Bye.
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 Bye. Bye.